Welcome back everyone. In this lecture, we will continue with bit more representation theory. So, first we will actually see this fundamental theorem of isomorphism. So, the very first isomorphism theorem that you must have seen in other contexts that says that whenever you have a homomorphism between two different G modules, so then if we take V modulo the kernel, that will become isomorphic to the image. So, let me state this. Okay. So, this is something you must have seen in other contexts like groups, rings and vector spaces. Now, we will actually see this in the context of G modules. So, we take GBLE algebra and V and W be G modules. Okay. Let us say we have a Lie algebra module homomorphism from V to W. So, this is a G module homomorphism. Then, so this is the given data. So, then we can actually define what is called kernel. So, which is naturally defined to be the kernel of this linear map. This is those vector in capital V such that which are mapped to 0 under this morphism phi. The second thing is there is this image, so which is defined to be the image of all the vectors, which is phi of V, V comes from capital V. So, the thing is the kernel will become G module. So, this is a G module and indeed it is a G submodule of capital V, and this image is a G submodule of capital W. So, now one can actually construct module structure on the quotient. So, this V modulo kernel phi. So, this becomes module for G and then this will become naturally isomorphic to image of phi. So, image of phi as a G module, we know that we have the G action. So, there is this natural vector space isomorphism that is actually comes from phi, induced from phi, from V modulo the kernel phi to this image phi. So, that vector space isomorphism is indeed G module isomorphism. Okay, what is the structure on this kernel? The quotient V modulo the kernel phi. So, that is easy to define. So, recall that the V modulo the kernel phi is nothing but all possible cosets V plus kernel phi, where V comes from capital V. Okay. Now, we define the action of G that is inherited from the ambient module V. So, how one can define for x in G and V in capital V. So, we define x acting on this V plus kernel phi is defined to be just x V plus kernel phi. So, this is how the action is defined. So, now it is easy to verify this indeed gives actually well defined action, because we are actually going modulo the kernel. So, if you take any two representatives, for example, we can take V plus some W1 and then V plus some W2, where W1 and W2 both come from the kernel. So, then it is easy to see that this action actually is going to give us V x of V plus W1, that is going to be x V plus x W1, which is same as x V plus x W2. Since kernel phi is indeed a submodule, okay. So, kernel phi is a G submodule of capital V. So, this I will leave it as exercise, it is not very difficult to prove. So, that tells you that xw1 and xw2 both are element of kernel phi. So, that means xv plus w1 is going to be equal to x v plus w2 modulo the kernel. Okay. So, that means even if you take any two representatives, the action of this G action is going to give you same answer. Okay. For example, we can take W1 to be 0, then we can easily see that xv kernel phi is same as xv plus xw2 kernel phi. So, the action is well defined. So, now it is a routine thing to check this is indeed a G module. Okay. So, I will leave it as exercise, check G acts on this V modulo kernel phi. That means we need to verify that. So, that whenever you take two element x and y from G, then if you look at the bracket x y, that acts as x composition y minus y composition x. Of course, that induced action we can denote it by phi tilde. Then what we mean by x composition y? Phi tilde of x composition phi tilde of y minus phi tilde of y composition phi tilde of x. Okay, that I am going to leave it to you to check. So, now we have a natural map which we are calling it phi tilde. So, which is a linear map induced from the linear map phi, which is defined from V modulo kernel phi to image of phi. Okay. So, it is easy to check image phi is also G module, that is all I am leaving it to you to check. Now, this map is isomorphism as a vector space. Okay. So, this is already bijective correspondence. So, this is linear isomorphism. So, that comes from actually the theory of vector spaces. So, now because we have G module structure on both sides, it is enough to check the phi tilde commutes with the G action. So, that is again easy to check because that is what happens in phi. Okay. So, let us write it down. So, whenever we have x in G and V in capital V, we have phi tilde of x applied on V plus kernel phi. So, this is something we need to check. This is exactly equal to x of phi tilde of V. Okay. The map is given by V plus kernel phi map to phi of V. So, that is the map. Okay. Again, one can check this is a well defined map, there is no problem. So, now, so what is x v plus kernel phi? X of v plus kernel phi is nothing but x v plus kernel phi. So, then phi tilde of this is going to be same as phi tilde of this. So, which is nothing but phi of x v, but phi of x v is going to be phi of x in x act on phi of v, because phi is indeed G module homomorphism. So, that implies that this is same as x of phi tilde of v. Okay. So, this simple routine check says that phi tilde is indeed G module homomorphism. So, that means the map that we have defined here is indeed G module isomorphism. Again, one can actually write down all other isomorphism theorem like second isomorphism and third isomorphism theorems and so on. So, I will leave it to you to actually check what it is. So, most important thing that I am going to state now, the submodule correspondence, that is what important. Suppose you have this map phi which is defined from V to W, which is a G module homomorphism. So, then we are interested in understanding the submodules of V containing the kernel and the submodules of W. Okay. So, let us assume that this map is onto for the simplicity, otherwise we can restrict to the image of phi. So, now we have the submodules of V that contains actually kernel phi. So, let us call it V dash. So, this is all submodules which contains kernel phi. Okay. These are all the G submodules. So, now from this set there is this natural map that actually takes V dash to phi of V dash. So, then this is actually mapping to let us say W dash, which are all G submodules of W. Okay. So, then you can see that there is this natural map that actually takes V dash to phi of V dash, and this map indeed one to one corresponds. Okay. So, the reverse map given by whenever we take W dash, then we just simply take phi inverse of W dash, and it is easy to check phi inverse of W dash is indeed G submodule. Okay. So, there is this lattice correspondence between the submodules of V which contains kernel phi and then so G submodules of W. Okay. So, what I mean by lattice correspondence, so this is a poset with respect to the containment. So, whenever we take V dash contained in V double dash, you can see that the image will be contained. So, it actually preserves the partial order. Okay. So, this is indeed lattice correspondence. Anyway, so this is indeed immediately follows from the fact that we have such correspondence between the vector spaces, and whenever we start with the G module, we end up getting G module on the right hand side, and whenever we start with the G module on the right side, we end up getting G module on the left hand side. So, that tells that this correspondence is there. So, this is something easy to check. So, maybe I will leave it you to check this. So, this is also I will leave it as exercise. Okay. So, now we define what is called reducible modules. So, we already seen some classes of modules. So, we have seen what is called indecomposable modules, and then we have seen what is called irreducible. So, basically first we define what is called reducible modules, and then the modules that are not reducible are called irreducible. Okay. So, that way we also define what is called reducible modules. So, we are going to see some interesting modules which are called completely reducible modules. Okay. So, here is the definition. Completely reducible, or sometimes they are called semi-simple representations. So, completely reducible modules in the module theory, or if you want to use the language of representation, they are called semi-simple representations. So, what are the completely reducible modules? So, your module V is said to be reducible, sorry, completely reducible. Let us say a module, of course, G module, capital V is said to be completely reducible, G module, if for any given proper submodule W, okay, for any given proper G submodule W, we have W dash, which is again proper G submodule. So, that just follows from W being proper anyway. This is proper G submodule such that V can be written as W direct sum W dash. Okay. So, this is indeed sum of actually vector spaces, but anyway. So, we are going to define the notion of direct sums. So, once we know what is the direct sum of modules, then indeed it says V is indeed direct sum of W and W dash, and this is should be true for all proper submodules G, W in V. So, there are actually many different definitions of complete reducibility available in the literature, and one can prove that all those definitions are actually equivalent. So, for example, I am going to actually prove one of the statement. So, let me just recall. So, what are all the other analogous statements are there? The very first definition is given in this definition. So, it is said to be completely reducible if for any given proper G submodule you have complement of the W. So, this W dash is called complement of W in capital V. Okay. So, given any proper W, we always have complement, that is what it says. So, if V is completely reducible G module, so then one can prove that V can be written as direct sum of irreducible submodules. Okay. So, one can prove that V is a direct sum of irreducible G modules. Actually, one can just take it to be submodules, not a problem. But what one can prove, we can actually have a weaker version of this. So, one can replace direct sum by just a sum, okay, and still the statement will be equivalent to completely reducible. So, V is just a sum of irreducible submodules. So, one can prove that all these statements are equivalent. V being completely reducible G module means V can be written as direct sum of irreducible modules. So, that is also equivalent to V is just being sum of irreducible modules. So, of course, we are assuming that all our modules are finite dimensional. One can make such statements for any module. Okay. So, this is actually kind of some general nonsense, but anyway we will do it for the finite dimensional modules. Okay. We assume V is finite dimensional modules. Okay. So, what I am going to do, I am going to actually prove that 1 and 2 are equivalent. I will leave it as exercise to prove that 2 and 3 are equivalent. So, it is easy to see that 2 implies 3. So, indeed what one can do, one can prove that 1 implies 2, 2 implies 3 and then 3 implies 1. Okay. One can try to prove in all possible directions. Okay. So, exercise maybe try to prove that 3 implies 1 and 3 implies 2, because 2 implies 3 is obvious, and then if you prove 3 implies 1, that way also one can get 3 implies 2, but anyway one can try to prove straight away 3 implies 2. So, we are going to prove only 1 if and only if 2. Okay. So, before actually getting into this characterization of completely reducible modules, So, let us see some examples and then try to understand what we mean by completely reducible. So, let us actually understand. Okay. So, if I take this G2, so this is the non-abelian two dimensional Lie algebra. So, this is actually naturally acts on C2, okay, because G2 is realized as 2 by 2 matrices inside JL2. So, now one can actually see that this is indeed reducible G2 representation. Indeed, one can take W to be the span of E1. So, let us say E1 and E2, this is the standard basis of C2. So, then if we take E1 span by E1, which is the W. So, this is a proper subspace of C2. Then one can easily see that E11 acts on E1 as just E1 with the eigenvalue 1. Then if you take E12, so which is acting on E1 will be 0, okay, just a simple matrix multiplication. So, that tells you that because G2 is span of E11 and E12, which is the non-abelian two dimensional algebra. So, it says that this subspace spanned by E1 is indeed submodule. So, this is G submodule of C2. Okay. So, I will leave it to you to check whether this has complement or not. So, the exercise, check W has complement in C2 or not. Okay. So, basically if C2 is completely reducible or not, you can actually check. If for example, W does not have complement, then that will imply immediately that C2 is not completely reducible, okay, because by definition of completely reducible, you need to have a complement for all of them. So, now let us see some other examples of representations. So, if we take any one dimensional representation, that will be irreducible. Okay. So, if we take Cn, which is can be regarded as representation of GLN, okay, GLN acts on Cn. Okay. So, maybe I can leave it as exercise. So, this is indeed irreducible action. Okay. So, this is a natural representation. So, prove that Cn is irreducible as GLN representation. So, one can also say that it is indeed irreducible as SLN representation. So, there is SLN naturally acts on this Cn. Okay. So, indeed one can make a very strong statement using what is called density theorem. So, if I start with a Lie algebra, let us say G, which is a let us say linear Lie algebra, which is sitting inside JLN. So, this is Lie subalgebra. So, then naturally G acts on Cn, okay, via the matrix multiplication. So, G acts on Cn naturally via matrix multiplication. So, now the question is when this Cn will become irreducible for G. Okay. One can answer that using the subalgebra, associative subalgebra generated by G. So, what is the statement? One can prove that Cn is irreducible G module if and only if when we take this associative subalgebra generated by G. So, that is going to be exactly the entire n by n set of all n by n matrices M1 of C. Okay, the one way is obvious. Suppose G generate as a associative subalgebra M1 of C, then Cn must be irreducible, because any submodule of G will be corresponding to the submodule of M1 of C, but there are no submodule other than like proper submodule other than Cn. The converse part, okay, so whenever Cn is irreducible as a G module, so then the subalgebra generated by G, it will become irreducible. Okay. So suppose Cn is irreducible G module, then that implies that Cn is irreducible as this subalgebra module. So, this is the associative subalgebra generated by G. Now, density theorem tells you that, so this is called density theorem. Density theorem says that this has to be exactly equal to M1 of C. So, this is one of the applications of density theorem. Okay. So, now you can actually check when Cn can be irreducible for some subalgebra G. So, now it is easy exercise to see that SLN actually generates M1 of C, okay, as a subalgebra, associative subalgebra. Okay. So, now we will actually give one simple characterization for modules being irreducible. Okay. Let us say G being a Lie algebra and V is irreducible G module. Okay. V is irreducible G module. So, then if and only if what one can prove for any non-zero vector V in capital V, if we take the submodule generated by this, submodule generated by V, then that has to be entire V, and this should be true for all vector V in capital V, non-zero vector capital in capital V. So, in that case V becomes irreducible, and conversely this happens. So, this is very simple exercise, I will leave it to you. So, let me now define what is direct sum of two modules. Okay. Let us say W1 and W2 are given G modules. So, then one can construct the direct sum of these two vector spaces. So, by definition this is just a pair, some u comma v, where u comes from W1 and v comes from W2. Now, what one can do, one can define the action of G, okay, for any x in G. So, you define this action x acting on u comma v by just x u x v, okay, for all x in W1, sorry, u in W1 and v in W2. So, then it is easy exercise to see that this indeed gives action of G on W1 direct sum W2. Okay. So, it is a simple exercise to see that G acts on W1 direct sum W2 via this star. That makes W1 direct sum W2 as a G module. Okay. And this is indeed called direct sum of W1 and W2. Okay. So, a module said to be direct sum of some finitely many modules W1 etc. Wk, if it is isomorphic to W1 direct sum etc. Wk. So, now it is easy to actually generalize this notion to any finitely many direct sum. Okay, I will leave it to you. So, now one can actually prove that what we promised. Okay. So, let us again. Okay. So, let us actually see some more examples before getting into the proof of complete reducibility characterization. Okay. So, here is some example, basic example. So, one can take dou n, which is the set of all upper triangular matrices, the set of all. Okay, let us take the diagonal matrices dou n, the set of all diagonal matrices. So, naturally this is going to act, okay, this is sitting inside GLN of C and this is going to act on Cn via matrix multiplication. So, now Cn you can decompose into direct sum of C1 etc. Cen, where E1 etc. En is the standard basis. Now it is easy to see that CEI is indeed one dimensional. So, in particularly irreducible dou n module. Okay. So, now using our characterization, you can see that Cn is indeed a direct sum of irreducible modules. So, that will imply that Cn is completely reducible module. So, that is also easy to check. If you start with any submodule, which let us call it V, so then it will have complement V dash. Actually, the natural vector space complement will give you the complement. So, this I will leave it as exercise. Now, use the definition directly to prove that this Cn is completely reducible. Okay, Cn is. So, this also implies Cn is completely reducible G module. Okay. So, now let us actually try to understand this for just one dimensional Lie algebra. So, if we take this G1, so I guess I used A1. So, if we take this A1, which is spanned by let us say Cx, so this is the one dimensional abelian Lie algebra. So, then if you look at its representation, so it will be a map from A1 to some GL of V. Okay, so, this is the representation. So, X is mapped to some XV. So, now there is no restriction, we can choose any operator and then send it to that operator and linearly you extend, then you get a representation. Okay, because Xx is 0, that is true, XV will become 0. So, that gives you representation. So, we have already understand that how actually isomorphic representations behave. So, if you want to actually get isomorphic representation, then the corresponding this operator should be conjugate. Okay. So, let us say let us identify this V with Cn. It is easy to work with a particular vector space, n dimensional vector space. Let us say I have actually just mapped this X to capital X. Then, so this is the map that is actually defines this phi x. So, then phi x isomorphic to phi y if and only if there exists G in GLN of C such that this G x G inverse becomes capital Y. Okay, because as a representation phi x and phi y they are isomorphic. So, that means Cn is isomorphic with respect to phi x. Okay. So, this just means that Cn phi x, this is the action that we are talking, isomorphic to Cn phi y. So, these two modules are isomorphic if and only if. So, this happens. So, that means we know that up to GLN conjugacy X can be transformed into Jordan form. Okay. So, that means up to this isomorphism one can actually conjugate this X to the Jordan form of X. Okay. So, this tells that the isomorphism classes of A1 representations. So, isomorphism classes of A1 representations has one-to-one correspondence between the Jordan forms of this n by n Jordan forms. Okay. So, now what corresponds to irreducible representation? So, it is easy to see that irreducible representations must be one dimensional. So, irreducible will corresponds to one dimensional representation. That means n has to be. So, this n also varies here. Okay. So, what will corresponds to completely reducible representation? So, completely reducible representation should be direct sum of irreducible representation, and irreducibles are one dimensional. So, completely reducible representations will corresponds to actually vector space, okay, the operator having eigenbasis. So, that means the operator must be diagonizable operator. Okay, diagonizable operator, because completely reducible means it is direct sum of one dimensional. One dimensional means irreducibles are one dimensional. So, that means by collecting the vectors from non-zero vectors from that, you can get a basis, eigenbasis of this operator capital X, whatever that is. Okay. So, completely irreducible corresponds to diagonizable operators, and irreducible corresponds to one dimensional representations. So, now you can see that if you are interested in cooking up some non-completely reducible representation, then you can start with some non-diagonizable operator. Okay. If I start with some non-diagonizable operator from this GLN of C, so then you will be getting actually not completely reducible representation. So, indeed this can be used to construct a non-complete reducible representation in this situation. So, let us say we have that G is not equal to the derived algebra GG. Okay. So, then one can actually construct the quotient, the G modulo the bracket GG. So, then this is indeed abelian algebra. So, now what we can do, we can actually pick, for example, some one dimensional quotient of this. Okay. So, pick I, which is contains GG, that has codimension 1 inside G. So, then we have this map G to G modulo the commutator subalgebra bracket GG derived subalgebra to G modulo I, and this is going to be the one dimensional Lie algebra. Then we can actually pick some operator, okay, let us say some capital X, which is not diagonizable. So, this X is mapped to this. So, then that tells you that this Cn is non-completely reducible module, reducible G modulo I module. So, now by pulling back, okay, pull back this. So, then that gives you non-completely reducible G module. One can easily prove that Cn is non-completely reducible G modulo I module implies G is non-completely reducible. Cn is non-completely reducible G module. So, that implies that whenever we have the situation G is not equal to the bracket GG, then we are able to get non-completely reducible module for G. So, in particularly this happens when we have G is, for example, solvable Lie algebra. Okay, for solvable Lie algebra, G must be not equal to GG all the time. So, what will be the other extreme? So, whenever we have G is semi-simple Lie algebra, in particularly for simple Lie algebras, so we always have, okay, this is a fact. If G is semi-simple, so then we have the bracket GG is equal to G. Okay. So, indeed in this situation we prove that Weil's complete reducibility theorem. Okay. So, this is the theorem of Weil. It says if G is finite dimensional semi-simple Lie algebra, then any finite dimensional module, any finite dimensional G module is completely reducible. Of course, the proof of this actually, like Weil's original proof uses some analysis coming from actually the study of Lie groups, but here we will be actually seeing an algebraic proof, and I will prove this result only for SLN. Okay. So, we prove this for only SLN. So, I am going to prove this for SL2 first, and then one can actually see how one can prove for SLN, because to get better understanding about general theory of representation, one should actually see everything how it goes in SL2. Okay. So, first we do it for SL2, SL2, then later for SLN. Okay. So, I will actually stop here and then we will actually continue with the characterization of completely reducible models in the next lecture, and then we will actually move to representation theory of SL2. Thank you. I will stop here.